Welcome to the Blueprint Room. Listen, as your chief architect for this explainer, my primary job today is to show you exactly how to build an absolutely unshakable, heavy-duty structural blueprint for Cambridge AS and A-Level Mathematics 9709. Specifically, we're locking in on the notoriously tricky terrain of Newton's laws of motion on inclined planes. Now, you might be wondering, why focus here? Well, most students lose incredibly easy marks when constructing their exam answers in this topic simply because their foundation is inherently weak. They treat it like a guessing game instead of an engineering project. Right now, in the drafting room next door, I've got two junior builders, Alex and Sam, and they perfectly represent the two most common architectural traps that students fall into. Alex? Well, Alex loves to stack up raw, heavy bricks. I'm talking about dumping raw facts and mathematical formulas onto the page without checking if the underlying steel frame can even support that weight. And then there's Sam. Sam wants to put up all these shiny glass panels and decorative features using fancy mathematical terminology before even cementing the core foundational columns. Both of these approaches lead to total structural collapse when the examiners run their tests. So today, we are going to lay down an unshakable thesis foundation. We're going to erect load-bearing analytical arguments, and we'll construct structural sentence connections that are guaranteed to survive the most rigorous Cambridge examiner stress testing. Put your hard hats on because we're getting right to work. Here are the strict schematics for today's build. We're going to start by laying the core foundations, move directly into erecting the procedural framework, conduct our evaluative stress testing, and finally, we'll wrap up with a site inspection of the most common examiner building violations.
All right, let's initiate phase 1. Laying core foundations and establishing our theoretical architecture, because you literally cannot build upward until your groundwork is completely set in stone. Okay, let's pull up a complex, high-tariff Cambridge past paper question right here on our digital drafting screen. Consider this our foundational challenge. Now, what's really fascinating about this concept of theoretical architecture is how it dictates your total exam survival. The theoretical architecture of this specific topic rests on 3 pillars: precise definitions, causal relationships, and cross-topic connections. You have to look at the principal examiner reports as our strict, non-negotiable building regulations. They explicitly highlight that candidates who reference cross-topic connections, for example, actively linking kinematics to dynamic forces, achieve significantly higher marks. But here is the trap, and I see Alex doing this all the time. Many students just try to build a solid, dense wall of math. They list every single definition of normal contact force without actually showing how it structurally relates to the problem at hand. Pure knowledge without causal relationships, that creates an incredibly brittle structure. So I want you to look at the blueprint screen. See that command word flashing? We need to isolate that. That is your command stress point. If the question asks you to evaluate or derive, and you build a purely descriptive structure instead of an analytical one, your building instantly collapses under the weight of the mark scheme criteria. You must align your equations perfectly to the exact command words of the question. The grid lines on your exam paper are there for a reason. Your paragraph columns must be aligned precisely to what Cambridge is asking you to build.
So the absolutely crucial point here is that a truly flexible foundation allows your mathematical structure to survive completely unfamiliar exam contexts without cracking. The syllabus emphasizes over and over that top-performing students exhibit a connected conceptual understanding that is highly transferable. Think about it. An unfamiliar context in an exam is literally like a sudden, massive earthquake hitting our construction site. What if the inclined plane suddenly features a varying coefficient of friction halfway up? Or what if the pulling force is suddenly applied at a totally weird angle to the plane? If your knowledge is rigid, if you've just memorized a step-by-step textbook process like Sam does, your structural integrity fails immediately. You have to deeply understand the causal relationships. Why exactly does the normal reaction change when the pulling force is angled? If you understand the why, well, congratulations, you've just installed high-grade shock absorbers into your mathematical building. You can adapt to literally any architectural curveball that Cambridge examiners decide to throw your way. Your structure will bend, but it absolutely will not break. Let's move straight to the next phase. Phase 2. The procedural framework and erecting the methodological scaffold. This is where we bring in the heavy machinery. Listen closely, because Cambridge actually demands this exact non-negotiable 5-step standardized sequence for processing Newton's laws on inclined planes. This right here is your methodological scaffold. First, identify the key elements. You need to map out the forces parallel and perpendicular to the plane. Second, apply the relevant principles, like correctly resolving that weight component. Third, execute the analysis, and this is huge, keeping your algebraic working visibly spaced like evenly distributed high-tensile rivets. Now let me tell you about a massive ironwork peer debate that just happened between Alex and Sam over this exact framework. They were at the drafting board trying to construct a model response. Alex wanted to fill the entire first paragraph with a massive cement block of terminology definitions, just totally overloading step 1 and 2. But Sam correctly argued that without leaving a hollow space for a dynamic counterargument or an evaluation of the forces, the structure has zero flexibility to hit those top band scores. So I had them rewrite their paragraph skeleton live. I told them if you just dump raw numbers onto the page and skip step 3's clear analysis, you're literally removing the load-bearing columns of your thought process. It makes it impossible for the examiner to award you marks because they can't see what's holding the roof out. After that, you move to step 4, verify your results, and finally, step 5, present it in the appropriate format. Sticking to these strict conventions, proper headings, correct terminology, and clear annotation is exactly how you erect an unshakable scaffold that maximizes your final point yield. Moving on to Phase 3, evaluative stress testing, focusing heavily on critical analysis and comparison. This phase right here is where we separate the basic, flimsy sheds from the elite, high-rise skyscrapers.
All right, blow the whistle, stop the clock, mid-build site inspection right now. Before we pour this final crucial layer of text concrete and secure this high-scoring paragraph framework, you need to make absolutely sure your construction line is permanently reinforced. So take a second, subscribe to Ace the Exams right now, and turn on all notifications to receive our weekly structural grade upgrades. Whether you are laying down an IGSC foundation or setting up a massive A-level skyscraper, this channel is your primary engineering grid. Got it? Okay, back to the build. If you construct a purely descriptive answer, I guarantee it will fail the evaluative stress test. You have to elevate it to the analytical level. Let's look at a highly specialized structural blueprint template that I always give my builders to help them do this. It's called the PEL methodology: point, evidence, evaluation, link. This is exactly how you rivet your raw data to your final evaluation. The point is your load-bearing column. You state clearly what changes, like maybe the acceleration is decreasing. The evidence is your steel crossbeam, bringing in the hard, calculated numbers from your resolved forces. Now you need the actual rivet, which is the evaluation, explaining the why. For example, detailing how the component of weight opposing the motion is increasing nonlinearly. And finally, you link it securely back to the floor joint, the core command word of the exam question. Upgrading from a simple, descriptive list of numbers to a fully analytical peel structure instantly, and I mean instantly, reinforces your entire construction line.
Now, during that earlier debate, Alex and Sam actually hit an unexpected structural roadblock right in the middle of their paragraph. Their evidence beam completely failed to latch onto their main thesis column. Why? Because they weren't using the right connective materials. To pass the Cambridge stress test, your comparative analysis must incorporate these specific structural supports shown here. Notice how high-scoring responses always use comparative connectives. To fix their draft, I had them rewrite the text out loud, line by line. Instead of just listing facts, they wrote, while the applied driving force remains constant in both scenarios, conversely, the frictional resistance differs significantly. Boom. That elegantly identifies similarities and differences. Then you have to support it with exact concrete evidence. In scenario A, the smooth plane yields 0 friction, whereas scenario B introduces a frictional force of exactly 15 newtons. See how that works? Finally, you draw a definitive conclusion about the relative importance of those forces. This is exactly what the Cambridge examiners mean when they ask for higher order assessment objectives. They want you to actively compare load-bearing capacities using strong, highly engineered structural sentence connections. If you don't use comparative connectives, your paragraph is just a pile of loose lumber. Final phase. Phase 4. Examiner building violations and avoiding structural collapse. We are bringing in the safety auditors right now to check your work. These are the 3 absolute most common structural failures that will instantly and completely compromise the integrity of your exam response. So we're going to do a live interactive site safety audit right now. I call this the viewer rebar stress test. Imagine a complex source data chart flashing on your blueprint screen at this exact moment. It's an inclined plane, there are 2 connected particles, a pulley at the top, a rough surface meaning friction, and a varying force applied at an angle. I am giving you a visual 60-second countdown timer in your head. You have to extract the single most high-yielding core metric needed to begin construction before the clock runs out. Ready? Think about it. The clock is ticking down. What is the absolute first load-bearing metric you need to find to prevent a collapse? Time's up. Listen, if your immediate answer wasn't extracting the normal contact force by resolving your perpendicular forces, your entire dynamic equation crumbles before you even pour the foundation. By missing that, you just committed building violation number 3, providing an answer that is not specific to the actual context of the angled force. Furthermore, even if you somehow guess the right number, but you completely fail to format and present it properly, like leaving vital structural components unannotated or dropping your units, the building inspector, which is your Cambridge examiner,
cannot legally pass your building. You will fail the inspection.
I want to emphatically, undeniably highlight this specific building inspector warning. Read this carefully. Even if the final calculation roof completely caves in, your visible method scaffolding will still earn you marks. Let me say that again. This is the famed method mark strategy. It is your absolute ultimate safety net on the exam construction site. In Mathematics 9709, marks are heavily awarded for the architectural process. Think about it like this. If you write out Newton's second law clearly, you substitute your resolved parallel and perpendicular forces correctly into the equation, but then you accidentally drop a negative sign in your final algebraic simplification, yes, your final answer will be mathematically wrong. The roof collapses. But because you left your scaffolding up, because you clearly annotated your steps, you used proper headings, and you showed the examiner exactly how you plan to build that equation from the ground up, the inspector will look at your site and award you the method marks. Never, ever erase your working. Don't hide your process. Let the examiner see the brilliant structural logic of your build.
So, as you take off your hard hat today, wipe the dust off your boots, and head back to practice your past papers, I want to leave you with this critical question to ensure your analytical foundations are truly unshakable. Can your current revision blueprint withstand the Cambridge Examiner stress test? Ask yourself honestly, have you been building fragile, easily broken descriptive paragraphs, or are you finally ready to construct heavy-duty, load-bearing mathematical arguments? Remember everything we've mapped out today. Implement the Peel methodology to rivet your evidence to your analysis, respect the strict examiner building codes regarding command words, and always, always leave your method scaffolding visible for the safety auditors. If you do this, your grades won't just stand, they'll tower over the mark scheme. Build smart, build incredibly strong, and I'll see you on the next site for our next explainer. Keep laying those bricks perfectly, engineers. You've got this.